Sklearncovariance. Description. The shrunkcovariance function is a technique used to estimate a covariance matrix that is more robust to noise and outliers than the traditional sample covariance matrix. This is particularly useful when dealing with datasets with high dimensionality or a small number of samples. The method works by introducing a shrinkage parameter alpha that controls how much the sample covariance is shrunk towards the identity matrix. Inputs: X, a NumPy array or pandas data frame containing the data to be used in calculating the covariance matrix. Each row represents a sample, and each column represents a feature. Shrinkage: a float between 0 and 1 indicating the degree of shrinkage to apply. A value of 0 corresponds to no shrinkage, the original sample covariance, while a value of 1 corresponds to complete shrinkage, the identity matrix. Outputs: shrunkcov, a NumPy array representing the shrunk covariance matrix. Shrinkage: a float indicating the shrinkage parameter used. Steps: calculate the sample covariance matrix using np.cov. Apply a shrinkage factor alpha to the sample covariance matrix by multiplying it with the identity matrix. This shrinks the covariance towards the identity matrix. Metrics: Leduit-Wolf shrinkage estimator. This estimator calculates the optimal shrinkage parameter alpha that minimizes the mean squared error between the estimated covariance matrix and the true covariance matrix. This is a common method for evaluating the effectiveness of covariance shrinkage. Visualization plots. Heatmap: a heat map of the shrunk covariance matrix can be visualized to show the relationships between different features after shrinkage. This helps understand the impact of shrinkage on the estimated covariances. Scatter plots. Scatter plots of different feature pairs can be used to visualize the effect of shrinkage on the correlation between features. This helps see how shrinkage affects the perceived relationships between variables. Fine-tune parameters. Shrinkage: the shrinkage parameter directly controls the degree of shrinkage. Increasing the shrinkage parameter will lead to a more shrunk covariance matrix, making it more robust to noise and outliers but potentially losing information about the true relationships between features. Finding the optimal shrinkage parameter depends on the dataset and the specific goals of the analysis. Uncertainty methods. Bootstrapping: the covariance matrix can be estimated using bootstrapping, which involves resampling the data with replacement and calculating the covariance matrix for each resampled dataset. This allows for estimating the variability of the covariance matrix and providing confidence intervals for the estimated covariances. Challenges and fixes. Challenge 1: over shrinkage. When the shrinkage parameter is too high, the covariance matrix may be shrunk too much, leading to a loss of valuable information about the true relationships between features. Sample use case: in a scenario where there are strong correlations between features, a high shrinkage parameter might incorrectly suggest that these features are independent, leading to flawed conclusions. Fixes to challenge 1. Experiment with different shrinkage parameters to find the optimal value that balances robustness and information preservation. Consider using data-driven methods, such as the Leduit-Wolf estimator, to determine the optimal shrinkage parameter. Challenge 2: under shrinkage. When the shrinkage parameter is too low, the covariance matrix might not be robust enough to noise and outliers, leading to unstable estimates. Sample use case: in a dataset with significant outliers, a low shrinkage parameter might result in a covariance matrix heavily influenced by these outliers, leading to incorrect conclusions about the relationships between features. Fixes to challenge 2. Increase the shrinkage parameter to improve robustness to noise and outliers. Pre-process the data to remove outliers or reduce their impact before calculating the covariance matrix.